Hello, good people. This is section 8.2 of Calculus Early Transcendentals, and we are doing applications of the integral, or applications of integration, and we're going to talk about the area of a surface of revolution. So we will be taking curves in the plane and either rotating them about the x-axis to form a three-dimensional solid, or we will be rotating about the y-axis to form a three-dimensional solid. And of course, since it is calculus and we have variable ranges, we are going through the limit definition of the integral, and we always start by dividing our interval from a to b into regions and equal regions, and we'll be making an approximation of that surface area. Okay, so we'll be calculating the surface area. And how will we do it? We always want to take an approximation using a surface area that we can calculate. And if you read your textbook or watch other videos, there is a derivation of how to find the surface area of the bottom portion of a cone. So if we take just one particular slice and we pull it out, we're going to approximate the surface area with the bottom portion of a cone. And it's called frustum. And there is a derivation in our textbook of how to calculate the surface area of that, and what it is your radius times the L, or the slant height. Our surface area of this portion here is going to be 2 pi r times L. And that L, being a slant height, if we turn it on its side, this would be our L up here, and our L is going to be arc length, right, or the ds. So you might see our delta surface area, and then our r is going to be from the axis of rotation, which in this case is the x-axis, is the axis of rotation. If we go up to our curve, it's going to be y, right, or f of x. So we might see that our delta surface area is going to be 2 pi, around the x-axis is going to be 2 pi y times the ds. And what is our ds? Our arc length. And from the last section, we knew that arc length is square root of 1 plus dy dx squared, dx. And in the case of function in y, it would be square root of 1 plus dx dy squared dy. Good, so around the and then in this case, if you see this formula before you, note that we are integrating with respect to x. So we would want to, with this y, substitute y equal to f of x. Now it is okay if you are given a function of y, so in other words, x is equal to g of y, or x is equal to f of y. You can go ahead and calculate your arc length with 1 plus dx dy and integrate with respect to y, and then in that case you would not be replacing the y, because you would just have an expression in that, and you can go ahead and integrate, but make sure that your limits of integration are on the y-axis and not on the x-axis. Okay, so let's do a couple examples here, and we've got find the area of the surface obtained by the surface area it's not even written correctly, but find the area of the surface obtained by taking that function and rotating it about the x-axis. So if we were to just draw a picture real quick, what does 2x plus 1 look like? It looks like a line in the plane. Here's my line in the plane. There's my f of x, and we're going from 0 to 5, and so this would be 0. This would be 5 over here, and we would be rotating about the x-axis, right? And so we would end up with another, and that would be our three-dimensional solid. And if I just take my arbitrary slice, here's an arbitrary slice, that's going to be the bottom portion of my cone. The L, my slant height, is there, and my radius goes from the axis of rotation up. And so I come over and I build my delta surface area is going to be 2 pi RL, and in this case about the x-axis it's going to be 2 pi y times the ds, and since I have a function in x, I'm going to say that that's going to be 2 pi times 2x plus 1 times the ds. And now I'm going to calculate the ds. So if I start with f of x equal to 2x plus 1, my derivative is going to be 2. My derivative squared is going to be 4. My 1 plus my derivative squared is going to be 5. And taking my square root of 1 plus my derivative squared is going to be the square root of 5. So my ds here is going to be the square root of 1 plus f prime squared dx, and that's going to be square root of 5 dx. Good. So now when I make my substitution, my delta surface area is going to be 2 pi times 2x plus 1 times the square root of 5 dx. And my total surface area is going to be the integral from 0 to 5 of my delta surface area, right? And so we're going to get 0 to 5 of 2 pi times the square root of 5 times 2x plus 1 dx. And that is a pretty straightforward calculation. And what is that calculation? So we would get 2 pi times the square root of 5, and the integral of 2x is 2x squared divided by 2, which simplifies to x squared. The integral of 1 is x, and now I'm going from 0 to 5. So now I want to do f of 5 minus f of 0, and I can keep my square root of 5 on the outside, and 5 squared is 25, and plus 5, and then take away 0 squared plus 0, and I end up with 50 on that inside, and 25 plus 5 is 30, excuse me, and 30 times 2 times root 5 is going to be 60. So we'll have 60 root 5 times pi is our arc length. Good. All right. I'm going to skip forward to this one. So when we rotate about the y-axis, then we're going to have a different r, right? If I take my function f of x and I rotate about the y-axis, we're going to take, again, perpendicular slices, and we'll still have that the slant height is still going to be our L, but now our R is going to equal X because it goes out from 0 to the curve. So we want to make sure that we are integrating, or that we form our 2 pi r times the ds correctly. And so now our r is going to be x instead of y. And notice here in this formula again, I've got an x here, but we're integrating with respect to y. So we would want to, when rotating about the y-axis, if we've got a function that is in terms of y, we would want to make that substitution so that we would have an expression completely in y. However, if we were given a function in x, we could, and we see here that we can keep that x there. If we're rotating about the y-axis, we can do the derivative, or the arc length, in terms of dy dx. Good. So this one actually should be, yeah, that's good. Okay, so let's find this example. And we start. So we've got a function x equal to y cubed, and we're rotating about the y-axis. We know that our delta surface area is then going to be 2 pi RL, which is going to be 2 pi x, because we're rotating about the x-axis, times the ds, right? And since our function is in terms of y, we want to call this 2 pi y cubed times the ds, and now I want to calculate my ds. Good. So I start off with my x equal to y cubed. My dx dy is going to be 3y squared. My dx dy squared is going to be 9y to the 4th. And my 1 plus dx dy squared is going to be 1 plus 9y to the 4th. And so if I take my square root, I can take my square root. So I know now that my ds is going to be the square root of 1 plus 9y to the 4th dy. Good. And I can substitute that value into my delta surface area. And so I'm going to get 2 pi y cubed times the square root of 1 plus 9y to the 4th dy. And then I can start my integration. And I see that I'm going to have a pretty straightforward integration. My surface area is going to be the integral from y equal to 0 to y equal to 1 of 2 pi y cubed times the square root of 1 plus 9y to the 4th dy. I see a straight substitution. If I let u equal 1 plus 9y to the 4th, then du here is going to be 36y cubed. So I can multiply by 36, and that means I can divide by 36, and that way I have my du in there. I can change my limits of integration when y is equal to 0, u is equal to 1 plus 9 times 0 to the 4th, which is just 1. And when y is equal to 1, u is 1 plus 9 times 1 to the 4th, which is equal to 10. So I can rewrite my integral as my surface area is going to be the integral of 2 pi over 36 is going to be pi over 18 from 1 to 10 of square root of u du, and the square root of u du is u to the 1/2 du. And now I can take my integral. So I get u to the 3/2 divided by 3/2, which is 2/3, and I still have my pi over 18. And I'm going to go from 1 to 10. Okay, my 2's cancel, right? My 2's cancels with 18 to give me 9, and I get pi over 27 times, and I can just keep that as 10 to the 3/2 minus 1 to the 3/2, and that's going to give me just 1. Okay. So in sum, just to reiterate, your surface area about the x-axis, you want to calculate delta surface area is going to be 2 pi y times the ds, and about the y-axis, we want delta surface area to be 2 pi x times the ds. So if you are given y equal to f of x, then your delta surface area, you'll want to substitute that y, and you'll want to say that that's 2 pi times the f of x, and we'll be doing the derivative 1 plus dy dx squared dx, so that everything is in terms of x. If you are given, and we also want to have our range of a less than x less than b, so that we're building something. If we're given x is equal to an f of y, then our delta surface and our y values go from c to d. We want to do our delta surface area, and it's still about the x-axis. We would say that it is still going to be 2 pi y times the ds, but our ds here, you can use 1 plus dx dy squared dy, and so you're not changing this y value into an f of x because we want to build the expression completely in y, right? So our surface area in this case would be from y equal to c, y equal to d of 2 pi y times that square root of 1 plus dx dy squared dy. Good? So you don't change it then in that case, and it's okay that you don't have to solve that function for y and then take dy dx squared. You can just go ahead and do the, you can calculate the arc length in terms of y. Instead, just make sure that your limits of integration are from c to d. Good? And similarly for the other side, you'll want to, this about the y-axis, we would want to, in the case of the, if you're given y equal to f of x, right, and we're going about the y-axis, we will still want to calculate our derivative, or I mean our ds as in terms of dy dx, right? Our ds would be the square root of 1 plus dy dx squared dx, and so we would not want to change the x. We would keep it as x, right? And if we were to have x equal to an f of y, we would want our delta surface area. It's still going to be 2 pi x times ds, but we'd be calculating, we'd want to substitute that value, and we'd want to say 2 pi times f of y times the ds, and our ds would be the square root of 1 plus dx dy squared times dy. And that way you get an expression completely in y. All right, hopefully that is clear. And next up is going to be more applications of integration, and that will be center of mass or center